Hi, in this video we're going to talk about the magnetization that happens in materials. So let's check it out. I've got some notes written over here on the left. Let's ignore that for just a little bit. Now, in our study of electric fields, we showed that the far field electric field of an electric dipole was given by this. So do you have to memorize this? Absolutely not. Should you understand it? Yes. Hopefully it's on your note card, bunny-eared in your book, or what have you. So let me just explain this again, just to refresh our memories. So this was the electric field by an electric dipole in the far field. An electric dipole has two charges, 2-point charges, of the same but opposite charge, plus q minus q, separated by a distance d. Okay, now if we wanted the electric field at a point far away from that dipole, say at point P, then this would be angle theta. And the electric field is given by what I have there. And we called P, which was equal to QD, P was the dipole moment. Now, interestingly, when we have a loop of current, so I'm just drawing my axes here, X, Y, Z, and let's say I have a loop of current oriented on the XY plane, centered at the Z axis, with current like that. We actually found the magnetic field due to that current carrying wire using the Biot-Savart law. And what's interesting, and we did not do this part, but if you looked at the magnetic field a far distance away, so far meaning in this case the distance away you are, that point P is from the center of the loop, is much larger than the radius of the loop. So if the radius of the loop is like 1 centimeter, we're talking about 10 centimeters, 20 centimeters away. The magnetic field, it turns out, when you're far away, you can make some geometric approximations, is given by this guy. I'll try to squeeze it in. Plus sine of theta in the theta direction, like that. Where m is the magnitude of vector m, which is I times s. I is the current in the wire. S is the surface area of the loop. And this is the magnetic moment, m. And if we look at this, we look at the far field of the far magnetic field due to this current carrying wire loop, and we compare it to what we said about the electric dipole, we see a lot of similarities there, right? The epsilon, the mu, the dipole moment, and now here we have a magnetic dipole moment, magnetic moment, 4 pi, the r cubed, and then the geometry is the same with the cosines and the sines. And therefore, what we can do is consider a loop like this of current carrying wire as a magnetic dipole. Now we know there are no point charges, but I'm just going to write Qm minus Qm like this. So we can consider this thing to be a magnetic dipole or a bar magnet, right? That's essentially what a magnetic dipole is. Now, okay, so how is that useful? Are we going to just always look at current loops? No. In an atom, an electron orbits around a nucleus, which is essentially the same as electrons moving in a loop of wire, right? And so we can consider atoms to be magnetic dipoles, each with their own magnetic moments. And further, electrons also spin around their own axis, which creates a second magnetic moment. So that's key there. There are two magnetic moments. The total magnetic moment of the electron is the vector sum of those two. Again, the electron is spinning around the nucleus, and it's also spinning around its own axis, and together that makes the magnetic moment of the electron. And by the way, this is also what gives the Earth its magnetic field. So now we know that materials, of course, are made up of electrons and atoms and so forth, and we wonder now what will happen to these magnetic fields created by the electrons if an external magnetic field is applied. So let me erase this for right now. And let's say we have a material, and at first, without an external magnetic field, its electrons are oriented just in a random way. I mean, that would be the best assumption that we can make. So here are my electrons, current carrying wires approximation, right? So let's say that this is my material, and they all have their magnetic dipoles randomly oriented, the atoms, that is. Now, there are three types of materials that we're going to consider, and so we're going to bring in these notes on the left, and everything that I'm going to run through here is confirmed by experiments. So this is just the way it is. The first type of material is the diamagnetic materials. And so what happens in diamagnetic materials is that the magnetic moments get oriented such that they are in slight opposition to the applied B field. So now remember we're talking about the magnetic moments are randomly oriented, and then we apply maybe a B field that's in this direction, a magnetic field that is. And so what happens then in diamagnetic materials is that the magnetic moments of the atoms align so that they are in slight opposition with B. And so you might consider, well, why is that? And the idea is that when B is not applied, the atom's magnetic moment is zero, because those two magnetic moments, remember, each atom is spinning around the nucleus, and each electron is spinning around the nucleus, and each electron is spinning around its own axis. So in diamagnetic materials, those two vectors cancel, and an external B perturbs the velocity of the electron according to what we've said in the past. The force on the electron is given by this thing here. Right? So then the velocity of the electron changes, and so now the two vectors will not cancel exactly, and so there's a little bit of what's called magnetic susceptibility, and that's, we use chi m, the Greek letter chi there, chi, chi sub m, and that measures this reorientation. We use chi e for polarization, electric susceptibility and polarization. Okay, so for diamagnetic materials, chi m is small and negative. So the small because there's just they align just slightly, and negative because they slightly oppose the magnetic field, the external magnetic field, that is. And examples of materials would be copper, diamond, germanium, gold, lead, and silicon. And this is not permanent. This effect is not permanent. As soon as we remove the B field, then it's reasonably assumed that the magnetic dipoles then just go back to being randomly oriented. Now then, the second type of material is this paramagnetic material, and what happens here is the magnetic moments get oriented in the same direction as the external B field. And the reason for that is because that under no external magnetic field, the two vectors, again, remember the electron spinning around the nucleus and around its own axis, it turns out they do not completely cancel in these types of materials. And so that leaves a small net magnetic moment. And so when you apply a B field then externally, then this has the effect of aligning these magnetic moments. And this effect is small, and it's not permanent. So this chi m is small in magnitude, and it is positive, so it's around, let's say, 10 to the minus 5. And some example materials here would be aluminum, oxygen, and magnesium. Now, the third type of materials, maybe the most interesting for our case here, is ferromagnetic materials. And in this case, chi m is thousands to hundreds of thousands. And this material, again, confirmed experimentally, requires a different sort of explanation, and which we'll get to in a second. And these types of materials are like iron, nickel, and cobalt. So here's the explanation, and it's basically like this: that the material consists of domains, and a domain is defined as an area in the material whose dimensions are a few microns, and they contain maybe 10 to the 15 atoms. And each domain has all of its magnetic moments aligned in the same direction. This is just confirmed by experiment. So in this domain, all of the atoms might have their magnetic moments pointing in this direction. And in this domain, all of the magnetic moments might be aligned in this direction. And maybe in this domain, you might have this direction, and this domain, you might have this direction. So again, this is like 10 to the 15 atoms all have their magnetic moments pointing in that direction. Now, what's really interesting here is that when you apply an external B field, like, I'm going to change the direction of the B field. Let's say we apply a B field this way. Then the domains that have their magnetic fields aligned with B, which is this domain here, will grow. So this domain actually grows at the expense of the other domains. So that's really cool. Now, if B, the external field, is small, it turns out that this process can be reversed, going back to the original orientation and size of domains. However, the interesting thing here is that when our external field is very large, and this domain is going to grow at the expense of the other domains, then that process is irreversible. And this is useful in computer information storage, like memory, hard drives, magnetic hard drives. Those are our three types of materials. Now, let us define magnetization precisely. And if you want to go back to polarization, I encourage you to do that maybe after this video. But magnetization we're going to define in a very similar way we did to polarization. So this looks a little strange at first, maybe, but I'll explain it in a second. This is measured in amps per meter. So in each of the three types of materials, we're going to let MJ is a vector, and also the initials of my favorite athlete. But anyway, MJ, we're going to say, is the moment of the jth atom. Okay? So what we do is we add up all of those moments across all of the atoms in a volume. Then we take that volume to a point by normalizing it by the area of, or the volume, normalizing it by its volume, and take that volume to 0. So we get to a point. So we can talk about the magnetization at a certain point. We did the same thing, or a very similar thing, to polarization for electric fields. Now, the magnetization creates a current. And we're going to call that current IB. And the B stands for bound. The current is bound to the domain or atom. So this is in direct comparison to what we said about free current or free electrons, about the the valence electrons, how they're able to move freely throughout the material. Here we're talking about bound current, and these are electrons that are bound to the structure of the material, and they're not free. Okay, so the M creates this current IB, and so we can write IB like this. Okay, and of course this is going to be equal to a surface integral, and we'll call it the bound current density dot ds. Now from Stokes' theorem, which relates a closed line integral, what we have over here, to a surface integral, we can write this this closed line integral as the surface integral of the curl of the magnetization dotted with ds. That must be equal to this same integral. Okay, and then we have the same surface, so we can compare the same integrands. We've done this a couple times already in this course. And we see that the curl of the magnetization is equal to the bound charge, or the bound current density. Now, as this is a current, we can add this current to the current in Ohm's law, or not Ohm's law, excuse me, Ampere's law. So Ampere's law was this in point form, and so now we can modify it to take into account the magnetization. So we would take J, which is the free current density, plus the bound current density, which is the curl, the curl, this should not be plus, curl of M, like this. Or, taking into account that H and B are related by the permeability, we can write this. Okay, and then this implies if I regroup this and take the curl out, then I've got B over the permeability of free space minus the magnetization equals the current density. And so now I can bring back H like this, right? Or we can write B now in terms of H plus M, the magnetization, like this. So what's key here is that the B field is, the magnetization affects the B field proportionally due to the permeability of free space. So you see we were able to factor out a mu0 from M, right? So that's key in this derivation. And then of course the magnetization term was absent in free space. So in free space M was 0, and we just had B is equal to mu0 times H. So that's not the case in materials anymore, and we're going to say that M is this chi M times H. Okay, and so with that definition then, we've already talked about the magnetic susceptibility, we can rewrite the B field like this. You see, and this is key, that everything is proportional here, and we get mu0 times 1 plus chi M times H, and it's this 1 plus chi M we call the relative permeability. And so finally we can write B as mu 0 times mu r times h, where mu r is the permeability. So you see, we can still use a similar equation that we did in free space. We just have to modify it a little bit to account for the magnetization of the material. Nice. Okay, so that gives you a basic idea about magnetization and how that affects the B field here. Now, in the next video, we're going to do something similar to what we did in electric fields. We're going to derive the boundary conditions, that is, how the magnetic flux lines behave at an interface of two different material, that is, two material whose relative permeabilities are different. So I will see you there.